multiple choice, and the 70% the other will be open-ended question. Probably it's a 5 to 6 question. So each of them will cover the aspects. So most of them are comprehensive. I'm not going to ask the memorization of the definition for such an open-ended question, but it will, such a basic concept will be covered by the multiple choice. Okay. And for Tuesday class, I'm going to cancel the Tuesday classes so you can study more for your midterm exam. Also, some of the students ask me what is the best way to study. The best way is a textbook and lecture. So lecture note itself is a supporting material. So if you just start with the PPT file, I don't think that's the best idea. Okay, so if you have the textbook is the best way. Even though there is almost 300 pages, but each page there is not very complicated, so you can study based on the textbook. Okay. Any question regarding to the midterm exam? Okay. So we will continue chapter 7. Couple of students asked me about whether you can extend the due date of the quiz. No. Okay. The schedule is a schedule, so I don't think there is a very difficult for the today's the banker's algorithm for your the quiz, so you can cover.
Also,
Yes.
is this any part will include in
Could
the
you?
chapter 7?
Yes.
Chapter 7, there is some part will include in the exam.
No. This is the
1 to 6.
final exam. So I think the last class we modeled the deadlock situation. So deadlock can be characterized by the 4 properties. One is a mutual exclusion. Only one process can take the one resource at the same time. In case the multiple instances for the same resource, it can be considered the multiple resource. Okay? And the hold one way, in case of the deadlock, the process should hold the process, then the wait another resource which is held by another process. Then no preemption is it cannot be reasonable, which means once it takes the resource and then the proceed further, which means until it get the resource waiting. And circular wait is such a there is the set of process, they are waiting each other, eventually they form a circle. It's a circular fashion. So we have used the resource allocation graph. In the resource allocation graph, we use this node for the process and resource. Process can be represented by the circle, and the resource can be represented by the rectangle. Inside the rectangle, there are number of small rectangles that indicate the number of instances. Then there are 2 types of edges. One is the request edges, which means when process I requests one of the instance of the R, that is from the process to resource. It's a directed edges. Okay, there is a direction. If assign one of the resource instance is assigned to the process, we can make another opposite direction of the arrow from one instance to process. Using such a resource allocation graph, we can represent the process and resource state like this one. If we can find any circle from the resource allocation graph, then may cause the deadlock problem. So we have seen the example last time. So basic idea is if we can find such as if we cannot find any circle in the graph, that's okay. So your operating system can proceed the next state. So in other words, you can grant for a process to take the resource. Otherwise, which means if you can find such a cycle or circle from the resource allocation graph, it may cause the deadlock situation. Not always. Sometimes even though you have the circle that doesn't mean it causes the deadlock situation. However, it may cause the problem, so you should take care of such a situation. There are three different ways of handling the deadlock. First one is deadlock prevention. Prevention means before the system allow the deadlock situation, and before system allow the resource allocating resource to the process, you need to check whether there maybe exist deadlock or not. There are two ways to prevent such a thing. One is a prevention, another one is avoidance. Prevention, in terms of prevention, we can prevent the deadlock by breaking one of the requirements that we have seen, which are exclusion, hold and wait, and circular, and whatever. So for one of them, if you can break one of them, that means there might be no deadlock. Okay? Example of them is a circular wait. So always, if your operating system always the process sequentially, okay? So which means if a process is taking the resource, then always until the process is completed, no other process can bother. So it's a linear. So there might be no circle. But so such a deadlock prevention sometimes it's not practical. Okay? So sometimes too many processes are waiting the resource or the process. So in terms of performance, it's not so good. The deadlock avoidance that we are going to discuss today is that before you grant the resource, allocating the resource for the process, you are going to check whether your operating system will be the safe state. Safe state means the operating system does not have any deadlock situation. How can we detect? We are going to use a resource allocation graph and using the Banker's algorithm that we are going to discuss. So Banker's algorithm, the idea of the Banker's algorithm is, can we find any sequence of the process? Okay, sequence of process by following the series of the process. The operating system never enter the operating system always safe state. So we will see the example today. So that means the first idea is never enter deadlock situation. Okay. In second state, you allow the process take the resource, so that may cause the deadlock. Okay. But whenever every time, every period time, operating system need to check whether there exists deadlock or not currently. Okay. Then if you can detect the deadlock and solve the problem. So that is the detection and the problem recovery. So that is the second approach. But most of the modern operating system use the ignore. That means the operating system. The reason why the operating system ignores such a deadlock detection, deadlock avoidance, deadlock prevention is it's expensive. It takes a lot of resources, it takes a time. So instead, operating system give the permission to the application or user to handle such a deadlock situation, which means if you encounter deadlock situation, until you do something, your application program is locked or hanged. Okay, so that is the method, three methods for handling deadlock. So we have seen the deadlock prevention and also deadlock avoidance. The idea of the deadlock avoidance is using we are going to manage the three primary information, that is number of available resources in your operating system, and also number of allocated is already had by the process. Then maximum demand of the processor. For example, process 1 needs 5 the hard disk drive. Then if you have the 5 available hard disk drive, then there might be no problem. However, so when a process needs 5 the hard disk drive, but currently it is taking 3 of them, and still 2 more needed. But if available is just 1, you should wait until the other process release such a resource. So that is the idea of the deadlock avoidance at the time if we can find any sequence of the process that can be terminated successfully, that the time there is no deadlock. However, if you cannot find such a thing, which means non-safe state, then they may pose the deadlock situation. So at that time, you are not going to allocate the resource. You are not going to grant the resource to be allocated by the process, which means the process cannot get such a resource. So safe state means that if you can find the sequence of the old process, where each process can take the required resource, okay, from the operating system, then this is called the safe state, which means it may not cause any deadlock situation. So this is a simple example that we have seen the last time. So we had three processes, P0, P1, P2, and the maximum need, which means to be completed, terminated, process 0 need 10 magnetic drive, and P1 need 4, P2 need 9. But currently, P0 used the 5 of them, and P1 used 2 of them, P2 used 2. The P2 is holding 2 magnetic drive, P1 is holding 2 magnetic drive, P0 need the 5 magnetic drive. They need 5 more, they need 2 more, they need 7 more. But right now, the available is total 12, but it's held 9 of them is held, so 9. So currently 3 of them are available at that time. Can you execute the P0?
Yeah.
No, because it needs 5 more. But right now we have the 3 available. What about the P2? It needs 7 more, so you cannot execute it. But P1 needs 2 more, which means P1 can be executed. You can grant the request of the P1. Okay, it is okay. So this time 1, this will available 1. Then currently 4, there's no more need, right? Then after P1 is completed, all needed return to here available. So it will be 5, right? Then P1 is okay. Next one is either P0 or P2. You can execute the P1 because it needs 5 more. That's enough in the available. So 5 will be granted to the P0. So P0 will be terminated. So no more need. This is a 10. Then after completed, 10 will be returned. So 10 will be available. Then it needs 7 more. So you have enough one. So it will be completed. Then 12. So with the order of P1, P0 followed by P2, your operating system is in the safe state, which means there is no deadlock situation. So you can grant the request of the resource by this order. However, what if you execute the P2 first? P2 needs 7 more, but you do not have enough one, so only 3 available, still waiting. That may cause the deadlock situation. So read this way, so you can avoid the deadlock. That's the deadlock avoidance. So to generalize this problem, we can have the Banker's algorithm. So before that, basic idea of such avoidance is that if you can find the safe state, no deadlock situation. However, if you cannot find the deadlock situation, which means the unsafe state, which means it may cause the deadlock. Not always. Sometimes it might be okay, as we have seen before, even though there is a circular way or the non-safe state, it may not deadlock, but it may be. So for our safe, in case you cannot find a safe state, which means unsafe, so at the time you avoid the request of the research from the process. To generalize such a problem to the multiple instances, in this case we consider only one resource, okay, and 12 instances. What if we have the multiple resources with the multiple instances? At that time we can consider Banker's algorithm. I don't know why it's named as a Banker's algorithm, but anyway, it's called the Banker's algorithm. Very, very well-known algorithm in the handling the deadlock avoidance algorithm. Okay. So in the resource allocation graph, so we are going to add one more edges, that is claim edge. Claim is the request. Okay? When a processor requests something, operating system check whether the request may cause the unsafe state or not. If you cannot find the safe state, in other words, if you cannot find the sequence of a process, which means it will be unsafe state. So you avoid, you decline the request, such a claim from the process. That is the deadlock avoidance. So if you believe that is okay, then you can assign. So request edge can be the assignment. So in this case, which means P2 is clean, the R2, and P1 is clean, the R2, same resource. If you allow, which means if you grant the request of the P2, which means then may cause the deadlock situation. Okay? Why? Because P2 is requesting the R1. But if you allow the request of P2, so R2 is assigned to the P2, then P1 is requesting the R2. It's a deadlock situation. So which means it's an unsafe state. At that time, you can decline the request of the P2. Then your operating system never enter deadlock situation. So how can we generalize such a problem? So in Banker's algorithm, we need to manage such information. First one is the available. So how many available instances per resource type? Okay. So for example, if we have the n number of available, n number of resources, okay, so which means we have the hard disk drive, and we have the memory, we have the magnetic drive, so 3, n is equal to 3. Then how many of them? 8. Hard disk drive 5, memory is 3, the magnetic 10. That time we can manage available as array, one-dimensional array to manage this information that is available. Maximum is the for each process. How many resources are needed on demand? The maximum. So for example, process 1 need 5, the 3 hard disk drive, and 2 memory and 8 the magnetic tape. Process 2 need the 3 hard disk drive and 3 memory and 10 magnetic drive. So how many process? You have n number of process. How many resource? You have the n number of resource. So it will be n by n matrix. Okay. Then next one is allocation. So right now currently P1 is holding 2 hard disk drive and 1 memory and 1 magnetic drive and 111, for example. This is currently held by the process. Then you can use n by n matrix to keep such a information. That is allocation. Allocation matrix means per process, per resource, how many resources the instances are allocated, held by the process. The last one is need. To be complete this process one, how many more hard disk drive? One more. And how many more memory? One more. And how many more magnetic drive? 7 more. So P1 need this. And also P2, 2 to 9 more. So you can manage this one using N by M matrix. However, you can actually calculate the need. The by subtract the maximum subtract by allocation. Then you may get the need. Okay, using such information, so we are going to use the information flow matrix to decide whether this is the safe state or not. So this is the algorithm. I will give the 1 minute whether you guys can understand this one. It looks like the complicated but very simple algorithm. But I know it's true sometimes if you see such a simple algorithm with a description, it looks like the complicated. Why don't you try to understand? So from the work and available finish. Finish means so whether process are completed or not. So it's the N by 1 matrix N array. So our goal is to find all the value of the finish is 1, 1, 1, 1, 1, 1. That is a safe state. Then we try to find the process. First, you do better terminate, complete the process that has the need. Okay? Need of the process is less than available. Right? So like this one. Need is smaller than available. Then you can complete it. Then you can return all the resources held by the process. Then you can have more available. Right? So the second step, in the second step, find the process. I means the process. Okay? Then among the non-finished, non-terminated first, then their need is less than work. Okay? Then the work currently had is the work plus allocation because allocated, then add it, then if finish it, should return to the available until you have the all completed, terminated. That's the idea. So why don't we use this example to understand such a interesting algorithm? So right now how many resource type do we have? 3. So M is equal to 3. So first one is A is 10 instances, and B is 5 instances, and C is the 7 instances. Let's say this is a hard disk drive, this is a memory, this is the magnetic tape. Okay, looks like it. And how many processes? So 5. So N is equal to 5. We have P0 to P4. Okay. Then the current right now in time T0. This is the current state. P0 has the first we are going to manage allocation. Allocation means it's held by the process. Right now, A, B, C is a hard disk drive, memory, and magnetic tape. 0, 1, 0. And P1, 2, 0, 0. And P2, 3, 0, 2. P3, 2, 1, 1. P4, 0, 0, 2. So which means currently P3 at time 0, P3 is holding the 2 of A, 1 of B, 1 of C, 1 hard disk, 2 hard disk drive, 1 memory, and 1 magnetic tape, and so on. This is the allocation. It's a N by M matrix. Also, maximum, they need to be completed, to be terminated. Each process needs, for example, 753. P0 need total 7 hard disk drive, 5 memory, 3 magnetic tape. And similarly, we 322, 902, 222, 433. This is the maximum need. If you have unlimited resource, you don't have to worry about this one. You can just allocate, okay, grant, and there might be no problem. But we have the only available A, B, C. Currently, we have the 322. How can you compute available? You can actually add up all of this. It's a 7. So 7. You have the total 10. 7 minus 10 minus 7. It will be 3. Okay. You have 3. So B is 3. So let's see. 1, 2. 2 of them are ahead. Then you have the 5. So 5 minus 2. Yes, it's a 3. So for each process to be completed, how many more resources are needed? So it's a need matrix, which means it's a maximum minus allocation, right? So which means 7, 4, 3. So which means the P0 need 7 more hard disk drive, 4 more memory, and 3 more magnetic tape. Okay, and similarly, subtract 3, 2. This is 0. Yes, this is 0. 3, 2, 2. 1, 2, 2. Max minus allocation 6, 0, 0. 0, 1, 1. 4, 3, 1. Okay. Then we can start the algorithm from, we are going to find the process. We are going to find the process. Their need is small, equal, or smaller than available. That makes sense. Then we can complete such a process. Which one? Process 0? No. It's a 7. It needs a 7. 1, 2, 2, yes. P1, maybe. And P2, no. P3, yes. P3, what is a P3? Yes. And P4, no. So either P1 or P3 can be terminated. So which one do we want? Let's start from the P1. So P1, it needs 1, 2, 2. So you can get the 1 more, the 8. So it will be 3. You can get 2 more B. It will be 2. You can get 2 more C. Then you don't need any more, and this will be
210.
you give 1. How many B did you grab? So 1, and this is a 0. Right?
No.
It needs 1, 2, 2. So 3, 3, 2. Yes. Okay, so it's the same, which means that it will be completed. Then all resource will be returned to the available. That will be, this will be 4, this will be 3, this will be 2. Okay, so P1 is done. The next we are going to find the process that satisfies with this condition, which means we can allocate, we can terminate this one. Which one? 4, 3, 2, no. This one is done. And 6, 0, no. 3, 4, 3, 1. So you can either this one or this one, P3. So if you did the same thing, 2, 1, 1 will be returned to the available. So this will be 6, 4, 3. So this is done. Next, we are going to find the next process that satisfies with this condition. This is not, this is done. This may be. So we will do the P2 first. So P2, so 302 will be returned. So 902. So next, yes, you can do the P0. Definitely, you can do the P4. You can find the sequence. You may find different sequence. As long as you can find the sequence, it is in the safe state. Okay. Once you find the safe state, you can actually allow run the request of the such a process, because you may not enter deadlock situation by following this order. So this is a deadlock avoidance. You avoid the deadlock by finding the sequence of process that are safe state. Okay. So this is the Banker's algorithm. Okay. So you can manage the need you calculate by the max minus the allocation. Then is it the same as that one? Maybe different. It's okay as long as you can find the sequence of process that keep the safe state. Then what if P1 request in 1, 2, so max minus 302 as a need. Okay. What was the maximum of the P1? 322. So 1, 0, 2. So max minus 3, 2, 0. 0 to 0. Okay. Then at this time, what if the process 1 request one more resource A, okay, and 2 more resource C, which means the 1 more hard disk drive and 1 more magnetic tape. This is a request. Then it needs 1 more A and 2 more C. So using this information, if you can find the sequence of process that are in the safe state, then you can grant such a request. Can you find such a thing? Then you can follow the same algorithm. So first, we can find the process. Their need is less than the available. Available is 230. It's a change. Available is a change because you use 1 more the resource A and 2 more resource C. Okay, so you have nothing on C. Okay, then first P1. So P1 is it needs the 0, 2, 0. So that is less than 230, right? So P1 can be terminated. After P1 is terminated, return the all available or allocated resource. Then eventually you can find such a process sequence. It may be different. It may be varied. Okay, you can find different sequence. As long as you can find it, it will be completed. What about the P4 request 330 from this? from this state 330. So which means, so available we have the 330. Yes, you can grant it, but what if you grant this request to the process 4, 330, process 4, 330, and what happened? Why don't you find? Why don't you try to solve the problem? So 330 for P4. So this time 0, 1, 0, 2, 0, 0, and 302, 211, 0, 0, 2. So maximum 753, 3, 2, 2, 902, 2, 2, 2, 433. So we have the 7, 4, 3 for need, okay, and 1, 2, 2, and 6, 0, 4, and 0, 1, 1, and 4, 3, 1. Okay, then available is right now 3, 3, 2. Then what if the P4 request 3 more A, 3 more B? Because you have available, you may grant to the P4. Then you need to check whether this grant may cause deadlock or not. So why don't you try? Why don't you apply the Banker's algorithm? So which means this one will be so 0, 0, 2, 3, 3, 2. Then maximum is a 4, 3, 3. So maximum, the need will be changed 1, 0, 1. Can you find after you grant the request of the P4? Can you find the process list? Then this should be changed. This is the current state. What is the first step? You need to find the process that satisfied with this one. Can you find the process? What about the process 1? You need 7. You can just take a look because you have nothing. So definitely this is not, this is not, this is not, this is not, this is not. No process can be terminated, which means these processes are waiting each other. It's a deadlock situation. It's an unsafe state. So which means you should have not grant this request to avoid deadlock situation. So this is the Banker's algorithm. What about? Yes.
The P4 request for 330, I think it's maybe for the maximum speed, not for the
330.
allocation.
So currently this is the state, then the process 4 requests 3 more, the A. Okay?
Yes,
So 3 more is the
maybe it's for the maximum need.
maximum is, yes, the maximum is 433. They need the 433. Then the current state is 0, 0, 2. Then this time, process 4 requests 3 more A. So 3 more A because you have the 3 more. And 3 more B, you have available 3 more. So it will be 3, 3, 2. Still, it needs 1 more A and 1 more C, which is to be terminated.
How do you get the P4 requested for 330? It's just an assumption or sudden requirement?
Oh, it's a event, okay? When at this moment, this is current information at time t0 and time 1. For example, after that, the what if P4 requests 3 more, okay? because to be terminated, it needs the more resources. So request 3 more the what is the A and 3 more B, then nothing for C. At that time, can we complete all the process? But your question is it the maximum, increase the maximum?
Yeah, I think the number should be added in the maximum, not in the allocation.
Let's
Because
see the question
P4
again.
Yeah.
Okay.
Because
Let's
the
see the
P4
question.
request 3 more A,
Mhm.
3 more B.
Yeah, that makes sense also. Check the yes. In the first case, the P1 request 102. 102. So 3 or to maximum 102. 3 or 2. No, at that time increase the allocation. Okay? So the question is, they are requesting the need, right? They are requesting the need to be completed. Okay, at that time, if you grant the operating system find the each processor will be granted first. If you can find the grant such a sequence, it will be a safe state, so no deadlock situation. However, the question is over here is what if you grant P4 first, can you find any sequence of the process that not in the unsafe state? That is the question. Okay? But I will double check, okay, whether that increase the maximum or the allocation.
Yeah.
But as far as I understand from the textbook, that is the question for allocation.
I think the allocation is the resource that
It's a head
is held
already
by
had.
the
Yes.
process.
Mm-hmm.
And P4 is requesting for 3 more A,
3
more
more,
B.
you mean
Yeah.
the increasing maximum?
But P4 is not holding
Mhm.
3 more A.
Okay,
and
I will check, but so far I understand there such a
Need should be there, like it requires, so
Mhm.
need should be increased.
need, and yeah, that is the same the idea as him. That if need is increased, that means the maximum. But I understand. My understanding is when they request the 3 more A, 3 more B, and 0 C, that means it allow the 3 more A, 3 more B from the maximum their demand. But I will double check. Okay. I will check, but this is based on my understanding. So if we can find such a sequence, yes. Okay. Because in need 7, 4, 3, which means the maximum is 7, 5, 3, 7, 5, 3, 7, 5, 3, 7, 5. Yeah, maximum is the same, so that means I think 102 P1, 102, 3, 2, 2, 3, 2, 2. I will double check. Thank you for comment. Then, anyway, so if you can find such a sequence of a process which are in safe state, they may not cause any deadlock problem, so you can grant such a request. Otherwise, you avoid such a request, then your operating system may not enter the deadlock situation. That is the deadlock prevention and deadlock avoidance. Second method is you allow any request, then check whether current state is in the deadlock or not. That is called the deadlock detection. You are going to detect the deadlock based on the current state. Then what if you can find such a deadlock situation? you need to solve the problem. Okay? So we will see how to detect it, and we will see how to address the problem. That is called the recovery scheme. So, how can we detect the deadlock situation? It's a circular way. Okay? So in other words, if you can find, in other words, we can use the banker side, if we can find process list, all of them can be completed, that means there is no circuit. Okay? So you can allow such a, there is no deadlock right now. So you can use the same idea of the banker's algorithm using available allocation and request to run the safety algorithm. It's the same thing. So I don't have to explain again about this one. So simply, so in this case we have the three resources, A7, B2, C6. So these are current status. There's no available one. So can we find any process list from here? Yes, because P2 and P0 can be terminated, right? Because it doesn't need any more resource. It can be completed eventually. Then after P0 or P2 is completed, 303 will be returned to the available. Then next time 303, which one? The P0 can be completed. So after P0 is completed, 313. 313 using 313, this one can be completed, and this one, then this one you can find the list of sequence, which means this currently there is no deadlock, so no problem. What if you cannot find such a thing? So for example, P2 has additional resource of the C, okay, which means P2 has the additional resource of C, which means even though you complete, P2 can be completed. You see P2? Oh yes, so it has the one more, P2 has the one more C over here. So I think the only option is a P0, right? Because you do not have available. So P0 is 0, 1, 0. Can you find any 0, 1, 0, less than 0, 1, 0? No, you cannot find. The next process, which means it may not in safe state. That means it is in unsafe state. Does it mean it's always a deadlock? No, you cannot guarantee. Sometimes deadlock, sometimes not. So with operating system recognize there might be chance there is a deadlock, so you need to solve that problem. How can we solve the problem for the recovery scheme? Idea is you need to terminate the process. So there are different options of the terminating process, kill the process. One is you can kill all the process that are involved in the deadlock situation. In previous case, you can kill the P1, P0, P1, P2, P3, P4. You can kill all the process. Or that's too risky because you need to kill all process. So you can kill one by one. First kill the process, then check the deadlock or not. Then if it still exists, then kill the next process. At that time, what can be the order of the killing such a process? So you can consider at that time different criteria, such as the lower priority process first. Or sometimes the total CPU time or resource. You can use the resource accounting information. You may kill the process that doesn't use a lot of resource, because when you restart the process, it may take the more resource. And also sometimes you can consider it's the same as the priority, which means the resource process needs to complete, and number you can consider number of the victim process. However, even though we can choose the select such a different scheme, basic idea is to minimize the overall cost. Then you can select the victim. Also, you should be careful. There might be sometimes starvation problem. Starvation problem is certain process may be killed every time, never been completed, terminated. So you should consider such a thing. The problem of such a deadlock detection or the banker's algorithm is their complexity is too high. Roughly, why don't you see this one? For each process, okay? For each resource, you need to consider process by process. Okay, for each process, you need to check the other process, which means it's an n squared. Total complexity is n times n squared. It's too high, too much complex. Think about the brute force algorithm. For loop, when you have the for loop, is n squared. Even that is very high complexity. Okay, which means when